Hello everyone and welcome to AP Biology with Mr. Jennings. So last video we talked about carbohydrates and what is a macromolecule, and today we're going to continue this with lipids. Now lipids are fats, oils, and waxes. Their primary function is long-term energy storage and insulation, and they're made of carbon, hydrogen, and oxygen. As you see noted here, not in the 1-to-1 ratio. It's more of an imbalance. Typically you see more carbon and hydrogen, then you see oxygen. And carbs, typically the carb, it's for every carbon, there's usually an oxygen. Usually, now when you get to the polymers, that number is a little distorted, but typically it's roughly a 1-to-1, roughly. That's in carbs. Now, in lipids, this could be really distorted. It could be 1 to like very little, like a decimal of oxygen. Some lipids don't even have oxygen whatsoever. So it does be shown that it can be without it. So don't be expecting you're going to see a 1-to-1 ratio or seeing oxygen every time. Sometimes those oxygens have been removed for the linkage purposes. Now lipids, like most things, can be subcategorized. The most common one is triglycerides, or at least the one that most people are aware of in terms of their health. And those are triglycerides. These are the ones that you see in your blood whenever you get a lipid count in your bloodstream. Triglycerides are 1 glycerol and 3 fatty acids. So let's talk about what that is here. So these long chains, these are what we call fatty acids. There are long chains of carbon and hydrogen and a couple other things here and there, but mostly carbon and hydrogen. Up here is where we see glycerol. Now glycerol is a little bit more complicated to talk about, but this is glycerol up here at the top. Now, when it comes to triglycerides, there's many different sub-classifications, and they typically are classified based on their bonding. A saturated triglyceride is one without any double bonds. It's called saturated because it has the max hydrogen for carbon. So carbon typically can hold at least 2 hydrogen and 3 if it's at the end, if it's a terminal carbon. When it comes to saturated, every carbon has 2 hydrogen and the terminal one has a third. Everything's maxed out, and because of that, saturated lipids tend to be very rigid. They're very long, rigid structures. Not much in terms of bending or flexibility. Now, unsaturated is like the name implies. It's not as saturated with hydrogen. That means there's a double bond somewhere. As you see here, we have a double bond right here. That double bondedness gives a little bit more flexibility because there's less hydrogens kind of inhibiting it. So if we were to draw all the hydrogen on our saturated here, physically it could not move as much. The hydrogens are going to repel off each other. On a double bond, there's less hydrogen to take up space, and there's a little bit more flexibility. And polyunsaturated is where there's multiple double bonds, as you hear. And because there's multiple double bonds, there's a lot more flexibility all around. Now typically, our solid fats, well, fats in general at room temperature, these are saturated. So as at room temp and it's solid, it's going to be considered a fat. That's where you're going to see saturated. If it's a liquid at room temperature, like an oil, you're going to see what's called an unsaturated. It's a little bit more fluid. It can move around just a little bit more, and that's how we get our oils. That's the primary difference between a fat and an oil. Waxes are similar, just the way they're made up. Now, probably the second most common, for at least what most of you have heard of, or at least you know it's a lipid, and one of the most important lipids is a phospholipid. Now, a phospholipid is pretty much a triglyceride, except one of the fatty acids have been replaced by a group called a phosphate. Now, phosphates are right here. Oh, excuse me. Phosphate right here. Phosphate is PO4, or sometimes with a PO3 and a negative. That means you find 4 oxygen around 1 phosphorus, and this is one of the most prevalent functional groups in biology. One of the ones we talk about quite a bit. It's very important. So phosphate replaces one of those triglycerides, one of the fatty acids in the triglyceride, leading to what we call a phosphate head and these little fatty acid tails. And this creates a thing we call amphoteric. So amphoteric means it has polar and nonpolar regions. Phosphate is a polar molecule. So this side here loves water. It's hydrophilic. The tails, though, is down here. They hate water. They will repel water at all costs, and those are called hydrophobic. And because they do not like water, they tend to form inwards. So if we were to drop a phospholipid collection, we'll drop a phospholipid into water, like so. Say you dropped a phospholipid in there. The phospholipid, instead of dispersing throughout, will form a ball where all the little tails, the little fatty acid tails, will point inwards to prevent themselves from coming in contact with water. This molecule here is very important because it's the main chemical compound that's found in all cell membranes. The phospholipid's unique chemical structure, being amphoteric, matters. Meaning, if it doesn't have that polar and nonpolar regions, you would not be able to form a cell membrane properly or get the function of a cell membrane properly. So it's very important that this exists. Now, the third classification of a lipid is probably one that you heard of, but you didn't know was a lipid. And that's steroids. And no, we're not just talking about anabolic steroids like you see in baseball and other sports. Steroids can be a variety of different things. They can be cholesterol. Probably didn't know that was a steroid. It can be testosterone, and it can be estrogen. Those are all notable steroids. These are a type of hormone, typically, except for cholesterol. Cholesterol is a little different. What makes steroids famous is, or at least notable, is this fused ring structure. They almost always follow this 4 fused rings. Now, the body can be a little different. And there's going to be different functional groups attached to the ends, and these different functional groups are going to result in different functions. So, for instance, most steroids typically follow this very basic guideline here. And cholesterol throws on a couple extra functional groups at the ends, and it allows it to be different kind of function. And even then, cholesterol has a variety of stuff there. You have those, the good cholesterol and the bad cholesterol. So all that does come into play. So to summarize here, lipids are one of the most important macromolecules in our body. Without it, you would not have your cell membrane, you would not have your testosterone, estrogen, or cholesterols. It does valuable long-term energy storage. Without it, you would not function properly. Waterproofing would not exist, you would not have cell transport, and obviously you wouldn't be able to actually even store energy for longer than a brief period of time because carbs do not hold it that long. Now, lipids do get a little bit of a beating because they're associated with fat. And yeah, if you eat a lot of lipids, you may develop a lot of fat. But lipids in themselves are not unhealthy. A healthy, balanced diet of lipids is actually good for you and keeps your body's nutrients in recycling. It allows you to have more building blocks of stuff because you're not creating new molecules most of the time. You have to obtain it somewhere. Now, the next video we're going to talk about is going to be proteins, probably the most complex of the macromolecules, and the one that spends a little bit more time on it, and really the basis for a lot of biology. So, keep touch, watch, and thank you for watching. Adios.